Right. So now I'm going to talk about the more general version of Ramsey's theorem. Now, instead of coloring edges of Kn, right? Edges could be seen as two subsets. Right? So when I say two subsets, that means subsets of size 2. What happens if we color M subsets? Can you still say something? Right. So let R of N1, N2, and K semicolon M be the minimum N such that for all N, if we color all M subsets of 1 up to N into one of K colors, then there exists I and an Ni subset X such that all M subsets of X have color I. And the theorem is, of course, this thing also exists. And the proof is also similar. First of all, we may assume the case 2, because if not, is less than this. So the first one is what does this mean? This means this is the number. This is the number that if no matter how I color the M subsets by 2 colors, either I guarantee there's a subset of this size having the first color or subset of that size of the second color. But if I have a subset of this size with the second color, then we are done. So therefore I can assume that I have subsets of this color. But if I have a subset of this color, then by induction, inside I can either, no matter how I color this by k-1 colors, I can find the Ni subset of color I, right? So this is easy argument, right? So as by induction, so I can assume that this number exists and that number exists. I mean this, right? I mean we assume that if the number of colors is smaller, then we already have a true statement. So now we only have 2 colors. So enough to show R of N1, N2, M exists. All right. Now let's pick one vertex, one number. And look at all other sets. Okay. Now, if I look at the set of size M here, then that induces a subset of size M minus 1. Right? Now, what we are going to do is to make sure that, I mean, we're gonna apply, of course we're gonna apply induction, right? And we want it, I mean, if this is big, so how big do I want? Like for instance, if this is as big as like Ramsey number of n1 minus 1 and n2 and m big. All right, so what does that mean? Yeah, so all right, let me go back. What I want is I pick one vertex V, and I look at all the sets of size m containing V, and that induces m minus 1 set. Now I apply Ramsey here. If this is bigger than Ramsey number of something and something with respect to m minus 1, right, then I'm gonna either, okay, let's say this is star, circle or star, then either we can find some big set of where all m sets containing V with this guy will have all the same color 1. Everything of this set, everything containing V and consisting of m minus 1 sets here will have a color 1. That's the first case. Or in the second case, I have a V here, or I have a big star. Well, in this set, every set of this type looks with the color 2. And if the first one happens, then I only need to make sure that all the m sets inside here has color red. And that's when I need Rn1 minus 1 and 2 m. What I mean is, if I have neighbors of size this big, then either I have a color 1 subset of size n1 minus 1 here, right? Which means that all m subsets of this set are red. Now, if I add this vertex, this point V, then all m subsets containing V and subsets of that will also be red. So that means I have a n1 set of complete red or color 1. I mean, by symmetry, same thing here, right? If this set is as big as this number, then either I have a color 1 copies of a set of size n1 whose all m subsets are color 1, or I have a set of size n2 minus 1 whose all m subsets are color 2, but in that case I can add V to extend it. So this means that we are done if n, no, we can find a copy. Yeah, so that means we may assume no, that means if n yeah, this number is less than or equal to range of n1 minus 1, n2, m, and n1, m2, m minus 1, right? So this implies that whenever I have this set. Whenever I have set of size this, then I can find, oh, but something, yeah, plus 1. Because I need a one vertex here, right? So whenever I have this number of vertices, no, elements, then I will find a subset of size n1 whose all m subsets of color 1, or subsets of size n2 whose all subsets have color 2. And I know by induction that these numbers exist because I'm gonna apply, yeah, so I should start the proof by saying induction on, well, not induction, think of the minimum count example. Minimum count example, consider the minimum count example with minimum m, right? So which means that if m is smaller, I assume that this number exists, and then minimum n1 plus n2. Okay, so that's why if this number is smaller, then I know that this number, Ramsey number, exists, and these two exist because their sum is smaller. Okay, so this shows that Ramsey number can be extended to set system, sets, and sometimes this is called the hypergraph. Okay. So instead of graph, now in the hypergraph, edges are any subsets.